anion and cation partners. And when you do that, the question is, do you see a product form? If you actually do the reaction, will you observe something happen? So here's the process we're going to follow. First, we're going to switch the anion and cation partners. We're going to make sure when we do that we write the correct formula, canceling the charges on the anion and cation, and then we're going to balance our chemical equation. Once we have our equation in hand, we're going to use the solubility chart that I gave you in class to determine if a solid will form or a precipitate will form. And we'll assign state symbols from that. Keeping in mind that if we don't form a solid for one of our products, then we don't observe a reaction, and we say that no reaction occurs when those chemicals mix. Here are two examples. Let's take a look at the first one. If we mix silver nitrate and potassium chloride, we're going to observe a double replacement reaction. Silver initially was combined with the nitrate, and so in the product it's going to be combined with the chloride. And our potassium, which had originally in our reactants been combined with the chloride, will be reacted with the nitrate. So I kind of have an inner and an outer set. I'll take my silver, and that's going to be reacted with my chloride. And when I do this, I need to make sure I'm thinking about my charges. Silver has a +1 charge, chlorine has a -1 charge, so those charges cancel and I don't need any subscripts. And then I'm also going to form potassium nitrate, and when you write your formulas for your ionic compounds, the positively charged ion needs to come first, your cation needs to be first. So checking charges, potassium has a +1 charge, nitrate has a -1 charge, so again I don't need to add any subscripts. If I look at this for balancing, I see that I have one of each of these elements or polyatomic ions on the left side and on the right side of the equation, so my equation is balanced. What I need to do now is I need to go back and check to see if I have solids or if I still have aqueous solutions when I'm done. So let's take a look for silver chloride at my solubility chart. Silver is a transition metal ion, so I'll put my left hand over here at transition metals. I have chloride for my anion. Where my fingers meet, when I draw them together, tells me what my solubility is. And this box says that these transition metal halides are soluble except for silver, mercury, and lead. Well, we've got a silver compound here, so that means silver chloride will not be soluble. It will become a solid. So I'll go back and add my state symbol of an S next to my silver chloride. We're going to check for the same thing for potassium nitrate next. Left hand on potassium, right hand on nitrate, draw them together where they meet. This is in the soluble region. If it's soluble, we will see it as an aqueous solution. And so I'll put AQ as my state symbol. And I do have one solid being formed, so I will see a reaction when I mix silver nitrate and potassium chloride. I will see solid silver chloride form. For the second one, I have sodium acetate, C2H3O2- is the acetate ion, let me remind you, and I'm reacting that with magnesium chloride in solution form. So when I go to write my products of this reaction, I'm going to switch my anion and cation partners. So I'll take my sodium and I'm going to have that react with the chlorine as a product for my double replacement reaction. And then my magnesium is going to be in an ionic compound with the acetate. So if I write this, I'll form sodium chloride. And sodium has a +1 charge, chlorine has a -1 charge, so I don't need any subscripts. And then I'm going to form magnesium acetate, magnesium C2H3O2. Checking charges, acetate's -1, magnesium has a +2 charge. At this point, you'll notice that these charges don't cancel. Magnesium is +2, acetate is -1. So I'm going to need 2 of those acetate groups in order to cancel the charge on magnesium. So I'll put my parentheses and a 2. I want to take a moment right now to point out that the subscripts don't necessarily transfer. On this first part of the equation, on the left side of the arrow, chlorine had a subscript of 2. On the right side of the arrow, it has a subscript of 1. Those subscripts are there to cancel the charges on the anions and cations. And so if you've changed what your anion and cation partners are, you have to redetermine any subscripts. Looking at this equation, it is not balanced. I've got 2 chlorines on the left, so I'll need to add a 2 in front of my sodium chloride. And then that gives me 2 sodiums. I'll need a 2 in front of the sodium as well. So I now have a balanced equation. What I'm lacking is my state symbols. So we've got sodium chloride and magnesium acetate to go and check with our solubility chart. Sodium chloride, soluble. Magnesium, here's acetate, soluble. These are both soluble compounds. Both of the products that would be produced by a double replacement reaction are soluble. And so this is aqueous. This one is aqueous. And I have no net reaction in this case because I won't see a solid form. The question is why do some solids form and while other ionic compounds will dissolve in water? And that's a question that's not answered by my solubility chart. My solubility chart is a set of empirical results. So what have we seen? Which things dissolve and which things won't? Let's take a closer look at what's going on when things dissolve to answer that question. And really it all boils back down to intermolecular forces because these ionic compounds have to be interacting with the water. We know from our previous discussion that water is a polar molecule, and most ionic compounds having charges are able to interact with that polar molecule. And that interaction takes the form of the water molecule separating the ions, the cation and the anion, and surrounding it, making little cages of water ions around those positive and negative charges. But there are times when, for a variety of reasons, the water molecules aren't able to effectively interact with the anion and cation of an ionic compound. In those instances, the attraction between the ions and the water just isn't enough to overcome the attraction between the ions themselves. The ions would rather stay together, clumped together as a solid, than be dissolved in the water. Energetically, it's just more favorable for them to stay as a solid. And so these are insoluble solids. They don't dissolve in water just because their interactions with water aren't strong enough to make that a favorable process. We are going to worry about our empirical results. We are going to focus on using our solubility chart to predict whether things will be soluble or not soluble. There are a variety of factors that go into determining whether things are soluble or not. And we're not going to focus in great detail on those right now. We're going to look more at the practical aspects of predicting whether a reaction will occur or whether no reaction will be seen.